Alrighty, I'm Robert from UT Austin, and today I will present our paper, Optimal Predicate Pushdown Synthesis, with, this is joint work with Eric, Dixin, and Işıl. Now, let's first consider this common scenario where we have a big chunk of data, which we feed into a potentially expensive computation, and at the end, after we obtain the output, we apply a filter to it. Now, the question is, what happens if most of the output just gets thrown away by the filter? In that case, why bother running the expensive computation at all? Well, a further question is, can we filter most of the data out before we even get to the computation? It turns out this is a well-known technique called Predicate Pushdown. It talks about moving filters before costly operators. It is also standard and well understood for SQL and relational algebra. And as covered in the previous talk, we move filters before joins all the time. It's considered pretty much solved for relational database. However, such classic pushdown falters at modern data pipelines written in general-purpose programming languages like Python or Scala. The culprit is user-defined functions, UDFs, that are essentially arbitrary stateful code that users write alongside these relational operators. Because these query optimizers treat UDFs as black boxes, they essentially throw up their hands and say, not my problem, whenever they get to these things. Let's take a look at a concrete example of what these pipelines look like. Here, we read data from a CSV file into a data frame, and then we drop null values from it. After that, we perform a per-group aggregation that essentially computes the top two scores of each team. After we obtain the output data frame, we merge it with a team's data frame. At that point, we apply a filter to the combined table that essentially keeps only rows with both top two scores above 90. At the end, we write to a CSV file. Now, let's focus on the last filter here and try to push it back all the way up through the pipeline. The first step is easy because we can push it to before merge because the filter only concerns attributes from the tops table. But here we run into a wall because classic methods treat UDFs like top two as a black box, so they cannot relate the filter to the input table. But what exactly is top two? Let's take a look. As I said before, UDFs can be arbitrary stateful code. And I would like to highlight three things that make UDFs hard. The first being internal state. In this case, top two tracks the first and second variables that hold the running top two scores. The second being that some UDFs tend to involve whole group reasoning, which is also in this case, which is also the case here, as any top two score only makes sense relative to others in the same group. Lastly, UDFs tend to have rich control flow in the form of loops and branching conditions. In this case, what we ideally want is to be able to split up this original filter P into two components, one that happens before the aggregation using top two, that does the heavy lifting to filter out all the irrelevant rows, and another component that happens in place after the aggregation that serves as the remaining cheap validation to ensure semantic equivalence. As a result, we are able to preserve semantics while requiring far less work on the part of the top two UDF. Now, with the UDF unblocked for pushdown, let's go through the pipeline again to carry out pushdown end to end. Again, we're able to very easily push the original filter P through merge, and then we're able to split it up into Q and P prime. And we can further move Q up to before drop an A because the score greater than 90 condition already rules out nulls. So yeah, that's the idea. And here's our goal. Our goal is to be able to do the following. For arbitrary code in the form of UDFs, we want to efficiently compute, verify it, and optimal pushdown at scale, pushdown splits. Here we have three concrete criteria. The first one is the correctness condition. We would like to rewrite the original pipeline into the optimized version where the predicate P is split into Q and P prime. And the next two conditions involve talks about optimality. We want Q to be as strong as possible because we want to filter out as much data as possible. Second, we want P prime to be as cheap as possible because we want to minimize work as well as to reduce redundancy with Q. So in the most ideal case, we want P prime to just be true, which is like nothing. Before we could get to automatically finding these pushdown splits, we first need to be able to check this equivalence. Here, we first recognize that predicate pushdown is fundamentally a program correspondence problem, where the original and optimized pipelines need to be related step by step. This is exactly what bisimulation is for, and we establish equivalence through a so-called bisimulation invariant I that relates the original and optimized runs at each intermediate step and at the very end. So here we see that I should hold at the beginning with the initial two states S0 and S0 prime. And as we step through the data frame, either keeping or dropping rows, I should keep holding. For example, when a row is kept, both the original and optimized runs step forward, and I should also relate the new pair of states. And if a row is dropped, only the original run steps forward because that row is filtered out in the optimized run. I should hold despite that. And so on and so forth until we exhausted the rows in the data frame. At this point, I should ensure that the two residual filters, P and P prime, that they agree on the two final states, S4 and S2 prime. And in the case where both P and P prime accept their respective final state, the two final states should be equal. And given the system, using this notion of equivalence via bisimulation, we're able to derive a set of 4 VCs that allow us to check whether I holds initially, whether it's preserved by every row, and whether it implies final state agreement. First, we have the initial condition that says I should hold on the initial states. And then we have a VC corresponding to the case where a row is kept, where Q holds on R and both the original and optimized run step. And then I should keep holding. The third concerns the case where a row is dropped, Q fails on R, and then only the original run steps, I should hold. Lastly, we have the final state agreement VC that says that I should imply one of two things, either both P and P prime hold on their respective final state and the final states are equal, or both of them reject the final states, in which case we don't care about what those final states are concretely. Well, looking at this system of formulas, one may wonder, why not use a CHC solver for this? Because it's a very common approach when you can encode these formulas as constraint horn clauses, and so you can solve for the unknowns using off-the-shelf solvers. Well, we don't do that here because we can't. There are two reasons. One is that if you look at the third VC, both Q and I, the two unknowns, appear positively, which means that these VCs are not in horn form. But even if they were, a CHC solver doesn't guarantee us the optimality that we want, namely that we want the strongest pre-filter Q and the cheapest residual filter P prime. So as a result, we have a hard predicate synthesis problem that require some custom synthesis algorithm that we developed. We use 3 key ideas in our synthesis algorithm to make sure that it's efficient. Namely structured search, unrealizability certificates, as well as root cause guided predicate repair. Let's begin with structured search. What I mean by that is that we untangle this 3-way coupled search into a layered pipeline where we first enumerate Q from strongest to weakest, and then for a given Q, we try to find the strongest by simulation invariant I that establishes its correctness. And only after that do we finally look into finding the weakest P prime. I would like to highlight 2 salient aspects of this flow here. The reason why we're able to isolate Q and I first before P prime is because only the first 3 VCs concern them. This allows us to focus our attention on what matters most. Because if you think about it, we care about the strength of Q the most, in a way. And also, we want to find the strongest I first because we know that given the shape of the fourth VC, where I occurs in the implicant, we know that if the strongest I doesn't suffice to show correctness for any valid, any P prime, then no other I would be able to do so. So we're able to terminate quickly. For termination, it's necessarily the case that we draw Q, I, and P prime from their respective finite predicate universe, which we construct using atoms extracted from the UDF as well as the original filter. And because we enumerate Q in order of strength, as long as whenever we find a valid Q paired with a weakest corresponding P prime, we already obtained the optimal solution. The next component to our algorithm is this unrealizability checking feature, where we need this because obviously for a lot of Q candidates, they could not be paired up with any valid invariant because they could be too strong, meaning that they would drop rows that could change the result beyond recovery by any residual filter. In this case, we would like to prevent wasting work on doomed paths, so we would like to know if Q is unrealizable at the start before exploring its whole subtree. We do this, we're able to achieve early termination by maintaining lower and upper bounds on the by simulation invariant throughout the algorithm. Here, concretely, we have I-min, which is lower bound, which describes what must hold for any any feasible invariant for the particular Q. And we have I-max that describes the most I can hold for any such invariant. And this bound will shrink as the algorithm progresses. If at any point the bounds cross, that means no invariant can work for the given Q. So we deem it as unrealizable, and we skip the whole subtree. Lastly, we have this notion of like root cause guided predicate repair, where we don't just blindly try to fix feasible candidates. We instead look at the concrete failure modes, for example, for candidate Qs. In this case, we check which VCs failed concretely and on what concrete row. And then we see if the VC failed because of keeping the row R or dropping the row R. If it failed because of keeping R, then we adjust Q to drop that row. If it failed because it dropped the row, then we adjust Q to keep it. And then after we obtain the repaired Q in this way, then we feed it back into the loop. Importantly, this step, such steps not only drops that particular candidate Q, but it also eliminates all candidates involving those offending atoms. Given all these ingredients, we implemented all of them in a tool called the Pushroo and evaluated it on a suite of 150 benchmarks involving real-world UDFs. And it turns out that Pushroo is really good. It is able to solve and infer optimal pushdown splits for 100% of them. And it's able to do so very quickly. The median synthesis time is 1.6 seconds, and it has a big impact on the end-to-end runtime of the pipelines. We see on average that the pipelines are sped up by 2.4 times, and at most we saw 2 orders of magnitude of speedups. And it's also good to highlight that prior work applies only to less than 15% of these benchmarks. So we're not even talking about like actually solving them. So thank you so much for tuning into my talk. Please check out the paper for more details. Here's the QR code for that, and please feel free to contact me for any questions.
All right, once again, we will take questions at the microphone, please. Oh man, everyone is immediately up asking questions, please. Go ahead.
Very nice work. I'm curious if you're able to push down user-defined functions past arbitrary user-defined functions, and if you looked at like parallel streams in, say, Eclipse collections or Java the standard library. Thanks.
I guess you meant pushing filter predicates down through the UDFs instead of pushing UDFs down through UDFs.
Well, the UDFs pass other UDFs, because you can imagine a predicate that also includes a UDF, right? That maybe filters things that are increasing based on the state. Would that be possible?
Yeah, so that's definitely not the focus of this work. We don't quite model that. We really consider filters as stateless in this work. So, but it could definitely be an interesting follow-up work to extend to that.
Okay, and the parallelism?
Yeah, I think that definitely, our tool definitely applies to that. I think we can perform pushdown with Pushroo in each chunk of the work, and recombine them if order doesn't matter.
Okay.
Yeah.
Thank you.
Thank you.
Hi, Justin Lubin, UC Berkeley. Thanks for the great talk. One thing I was curious about is the bisimulation invariant data dependent, or are you trying to prove that the programs are going to be equivalent for all possible input data sets? Seems like you might be able to get some like coarser notion of equality.
Yeah, I forgot to mention that. Let me go back. I forgot to mention that all the VCs are universally, like the S and R variables are all universally quantified.
And have you thought about making it like data dependent?
Yeah, in fact, during development of this work, at various points it seemed to be the case that having the users provide, some like assumptions or on the shape of the input data would help unlock more opportunities. But we decided that for now we want to have a cleaner theory and just keep it at this. But that's definitely an interesting follow-up work. Yeah.
Thanks.
Hi, AJ Root from Stanford. Great talk and cool project. I just wanted to ask, so in database management systems, there are some cases where predicate pushdown is actually not preferred. Like you would not push a predicate down past a join in the case of like the predicate being extremely expensive, like some sort of like regex expression on strings.
Yeah.
Do you ever see in your benchmarks that predicate pushdown actually like decrease or reduces negatively impacts runtime?
Absolutely.
Does that happen in your benchmarks?
Yeah, absolutely. There are cases where we see like negative performance increase.
Okay. So do you think there's a way like to incorporate some sort of cost model of like what optimality means to make like a cheap predicate pushdown? You
touch on a really good point. Definitely. We can definitely involve all the prior work in the database community on cost models. Currently, we only use logical strength as our sole criterion, but that's all because we want like a elegant theory for a start. But yeah, we can plug in, like for example, looking at the number of like the concrete shape of the predicate, for example, or we can take some off-the-shelf like cost model learned previously in our domain. So yeah, it's definitely possible.
All right, cool. Thanks.
Mm-hmm.